Lighthouse Scientific Education presents a lecture in the Energy series. The topic: Thermodynamics and Advanced Concepts. Material in this lecture relies on an understanding of the previous lectures, energy and reactions, thermochemistry, and bonding, an overview. Specifically, this lecture is an extension of the material in the Energy of Reactions lecture, and as such, it begins with a brief review of some of the topics of thermochemistry. It is where the term work is first discussed. From there, the concept of state function is explored. What we know about enthalpy will be expanded in context of the state function. Two new thermodynamic quantities are introduced: entropy and Gibbs free energy. With these two new quantities, we can discuss the first and second law of thermodynamics. The last part of the lecture is given over to more advanced concepts. The whole subject of thermodynamics is an advanced one, but there are materials that not all students will need to be exposed to. Make sure you understand what material is covered in your class. The first advanced concept is Hess's law, and the second is the enthalpy of formation. Energy, specifically heat or thermo, is broken down into two lectures in this series. The previous lecture covered thermochemistry. It is a branch of chemistry concerned with the study of exchange of energy or heat in a chemical reaction or process. This lecture looks at thermodynamics. It is a branch of chemistry concerned with the exchange of energy and work in a system. There is considerable overlap between the two branches, but the key term that separates them is work. We will get to that concept later in the lecture. A discussion on thermodynamics and thermochemistry generally contains the concept of a state function. That concept, however, requires us to be familiar with several definitions from the previous lecture, dealing with energy in reactions, as well as a couple new ones. The first definition is the system. It can be a physical space or a conceptual one. Regardless, it is a collection of matter within a fixed set of boundaries. Contrast system with the term surrounding. It is everything outside of the system. Any piece of matter is either in the system or it is in the surrounding. As such, the universe is composed of the system and the surroundings. What determines the type of system is whether energy or matter can be transferred between the system and the surroundings. The internal energy of a system, given the designation of capital U or capital E, we will use E, is the total energy of the system. There are two parts to this energy. One is a form we've already discussed, heat, designated by the letter Q. It is the amount of thermal energy transferred into or out of the system. As for types of system, three types were demonstrated in the previous lecture, using flasks as examples. They are called open, closed, and isolated systems. In an open system, there is the possibility of exchange of heat and an exchange of matter between the system and the surroundings. A closed system can also have the exchange of heat, but not matter. A lid on the flask sees to that. An isolated system allows no transfer whatsoever. It is more of a theoretical system, but a temporary one can be produced by wrapping the sealed flask in some sort of insulator that dramatically slows down the loss or gain of heat. Returning to the internal energy and heat, there is one more component to energy that needs to be introduced: work. It is an old familiar term that will be used in a new way. In chemistry and physics, work is the energy it takes to move an object against a force. Mathematically, that is, work equals the force applied to an object times the distance the force moves that object. In thermodynamics, work is more generally taken as the capacity to move. It doesn't matter whether the work is productive. It only matters that there is movement due to a force. Work can be defined in terms of its action on a system and its surroundings. Work is defined by its flow between the system and the surroundings. Work is considered negative when the system is doing the work on the surrounding. If the surrounding is doing the work on the system, then work is considered positive. Negative and positive have nothing to do with the distance moved, as found in the definition, but rather the direction of the work from an energy perspective, into or out of the system. With this level of understanding of energy in the system, we are ready for the concept of a state function. State function is defined as the property of a system that only depends on the initial and final state of the system. That is, from some initial time to some later time. Another way to say this is that a property that is a state function is path independent. It doesn't matter what energy the property has between the initial state and the final state. The only thing of concern is the difference in energy of the properties between the two states. A useful analogy for thinking about state functions is following a hiker going down a mountain from point A to point B. We'll call point A the initial or starting position, and point B the final or ending position. A look at a map will tell us the difference in height between the 2 points. However, mountain trails are not straight lines, and neither is the energy profile for a chemical reaction. So a real hike is some meandering path dictated by the terrain. The difference in the height between points A and B has not changed, even though the path went through a lower height. Now, let's say there's a second path along the mountain. Even though this path takes longer and has more extremes, the state function, the height difference, our analogy to state function, between points A and B is not changed, path independent. State functions come up in chemistry with chemical reactions. The energy of the reaction only depends on the energy of the initial state and the energy of the final state. The study of energy gets to, for the most part, ignore the actual chemistry, the breaking and forming of bonds, and only focuses on the energy difference between the two states. This greatly reduces the complexity of the reaction. In this lecture, we will look at 3 state functions. We will review enthalpy and introduce entropy and free energy. Importantly, work is not a state function. It does depend on the path, since distance moved is in the definition. The one state function that we have come across before is enthalpy, capital H. Its thermodynamic definition is the internal energy of a system plus the product of the pressure and volume. That is the precise definition, but there are more useful ones to our study, including enthalpy being heat transferred under constant pressure, and enthalpy being heat content or total heat. As a state function, enthalpy is usually represented as a difference, or a delta H, in a chemical reaction. Delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. The heat energy of the final state minus the heat energy of the initial state. This matches the process of getting a height difference in our hiking analogy. There are 2 important terms associated with delta H, and they are related to the release or consumption of heat energy. These terms were initially discussed in the previous lecture. The phase transition of water serves as an excellent example equation. One process is going from liquid water to solid, freezing, and the other is the reverse, going from solid water to liquid, melting. One process releases energy, and the other one consumes it. In freezing, there is a release of heat. Such reactions are said to be exothermic. A lookup table provides a delta H value of negative 6.01 kilojoules per mole. The negative sign says heat is released. The opposite reaction, melting, heat is added to the reaction. This is an endothermic reaction. The delta H associated with this reaction is the opposite of that of the freezing reaction. According to the law of conservation of energy, energy cannot be created or destroyed. The gain of heat on one direction is equivalent in size to the loss of heat in the other direction. Our understanding of enthalpy will be an outline for the discussion of the other state functions, beginning with entropy. Entropy, capital S, can be a little harder of a concept to grasp. Its rigorous thermodynamic definition is the thermal energy per unit temperature that is unavailable for doing useful work. Friction is an excellent example of such an energy. Almost every motion has some loss of energy to friction. That energy does not get put to work. Motion creates this friction energy. A more useful way to consider entropy is disorder. Entropy is a measure of the disorder of a system. We get that heat is a flow of energy. Things get hotter. But that things get more disordered is also an energy flow? This is certainly a harder concept to wrap one's head around. For a process or a reaction to be favorable from an entropy perspective, the final state has to be more disordered than the initial state. Often the term random is used for disorder. Delta S equals the entropy of the final state minus the entropy of the initial state. The final and initial state is consistent with the product-reactant pairing of the change in enthalpy. The enthalpy of the product minus the enthalpy of the reactants. While before and after, initial and final, or reactant and product can be used with any of these state functions, interpretation of the delta values differ between these two in one important way. That is in how the sign of the value determines favorable and unfavorable. These are related to spontaneous and non-spontaneous. As we just reviewed, delta H is favorable when the change in energy is less than zero, when it is negative. That is exothermic. Delta S, however, is favorable when the change in disorder is greater than zero, when it is positive. The reason a positive delta S is favorable has to do with how entropy is defined. It is defined as disorder. It is favorable for a system to become more disordered. If, however, the definition had been the amount of order and not the amount of disorder, then a favorable delta S would be negative because favorable would be the loss of order. The loss of order is disorder. So an increase in the loss of order is an increase in the disorder. Yes, it is easy to get lost in the corridors of thermodynamics. An example will help move this understanding along. Say we have a deck of cards. The cards are in a stack. The stack is an ordered structure. It takes work to get the cards in a stack. But leave the deck sitting on the table, and after some period of time, they will most assuredly become disordered. Given enough time, the deck will always tend to disorder. It will never, on its own accord, reform back into a stacked deck. Why is that? Entropy. It may have a confusing definition, but we know it when we see it. Things naturally go from neat to messy, from one whole to many pieces, and not the other way around. On a molecular level, the entropy of a molecule is related to the modes or kinds of motion available to the molecule. Not all molecules are equal in this context. A real molecule is not stiff and unmoving like it is in a picture of a model. Modes available to a molecule include translation, like a gas molecule zipping around, That's translating across space. And then there is rotation. Spinning around is disorder. The more ways a molecule can spin, the more disorder is available to it. Another mode is vibration. Bonds can be thought of as springs, and bouncing back and forth in the bond is disorder. Students are not asked to do anything with these modes of motion, except to note that the motion is the origin of the disorder. More options for motion means more available disorder. There's a formula description of entropy. Straight from the definition, it is S equals Q over T. This is the ratio of heat to temperature and is another aspect of thermodynamics that students will have minimal exposure to. Entropy is a tough subject. What is usually expected of the student is an understanding of the definition and some familiarity with these two formulas. The last state function in this lecture is Gibbs free energy, capital G. It is a measure of chemical energy. G is the energy associated with a chemical reaction that can be used to do work. The concept of work is making its way into our study. G is a broader term than enthalpy and entropy. In fact, G relates the enthalpy and entropy of a system. One of the most important formulas in thermodynamics is G equals H minus T times S. Enthalpy minus temperature times entropy. Like in gas law, temperature has to be in Kelvin. Like with enthalpy and entropy, a change in state equation can be produced for Gibbs free energy. Delta G equals the free energy of the products minus the free energy of the reactants. These three delta equations can be combined along with G equals H minus T times S to form another delta equation. Delta G equals delta H minus T delta S. This form of the delta G equation is used extensively in more advanced chemistry courses. Our investigation will not be that extensive. We will look at delta G, where it reveals the foundation of energy in a chemical reaction. But first, we will use these two delta G equations to tie up our discussion of reaction coordinates and energy in reactions. Bringing back our example coordinate, but with Gibbs free energy on the y-axis, we have a reaction with the energy of the reactants being higher than the energy of the products. As the reaction proceeds, it releases energy. The delta G of this reaction is negative, but that negative value cannot be specifically attributed to changes in the enthalpy or entropy, as seen in this equation. All we can gather is that there is a release of energy, as seen with this equation. Since there is a release of energy, the reaction is said to be spontaneous. Favorable will also work. Remember, spontaneous does not mean fast. It only states that given enough time, the reaction is expected to occur. Now, take the reverse of that reaction. It will only proceed to completion if there is an addition of energy. The amount of energy added is equal to the amount of energy released in the spontaneous version of the reaction. Another example of the law of conservation of energy. The change in free energy for this direction of the reaction is positive, since products have a higher energy than reactants. This reaction is non-spontaneous or not favorable. This is the role of Gibbs free energy in a chemical reaction. We can now take a closer look at the second form of the delta G equation. For a reaction to be favorable, negative delta G, it has to have the right combination of the exchange of heat, enthalpy, and disorder, entropy, of the reactants and products. So it's not as easy as saying that a reaction is always favorable if it's releasing heat, negative delta H, because there is still the disorder factor to consider. And let's not forget the negative sign and the temperature, T. there are a lot of moving parts on this one, so a table that contains the energy terms and their connection to spontaneous will be helpful in providing some understanding. Spontaneous is determined by the sign on the charge of delta G, which itself is based on whether the enthalpy and entropy have a positive or a negative energy. A quick point before we start. If delta S is positive, then minus T delta S is negative. A positive times a negative is a negative. If delta S is negative, then minus T delta S is positive. A negative times a negative is a positive. With that somewhat straightened out, we can fill out the table. Question: is a reaction spontaneous if both terms, change in enthalpy, change in entropy, are positive? Since delta S is positive, minus T delta S is negative. Looking at the equation strictly from a math perspective tells us that spontaneous depends on the size of the terms. If a positive delta H is larger than a minus T delta S, which as a term is negative, then delta G will be positive. The positive delta H wins out. If, however, the negative term minus T delta S is larger than the positive delta H, then delta G will be negative. With this arrangement of energies, delta G is negative and spontaneous if the minus T delta S is larger than the change in enthalpy. Another possibility in a reaction is for delta H and delta S to both be negative. Under these circumstances, the minus T delta S term is positive. Negative times a negative is positive. So if the positive value term minus T delta S is larger than the negative enthalpy term, then delta G is going to be positive. The larger term wins out. On the other hand, if the negative delta H term is larger than the positive value minus T delta S term, then delta G will be negative, and the reaction is spontaneous. Under this limitation, the reaction is spontaneous if the change in enthalpy is larger than minus T delta S term. In these first two rows, we are simply looking to see which of the terms is larger, and that decides the sign on delta G. Easier to follow is if the change in enthalpy is negative and the change in entropy is positive. This order goes up. The minus T delta S term is therefore negative. If both terms in the equation, delta H and minus T delta S, are negative terms, then delta G has to be negative. When is an equation with a negative delta G spontaneous? Always. The system is releasing heat and becoming more disordered, both favorable. The reverse has change in enthalpy as positive, absorbing heat, and the change in entropy as negative, becoming ordered. That puts the minus T delta S term as a positive term. If both terms in the equation, delta H and minus T delta S, are positive, then delta G is positive. When is an equation with a positive delta G spontaneous? Never. If the reaction consumes heat and produces products that are less disordered, then it is unfavorable on two counts. So, energy turns out to be a sign-sensitive way to look at reactions. An extremely informative way, but not always intuitive. It does, however, begin to make more sense the more one sees it. The other major topic with thermodynamics are its laws. We will look at two of them. The first law of thermodynamics is concerned with the change in the internal energy of a system. It is an extension of the law of conservation of energy. No energy is created or destroyed. It is only moved around. That means the total energy of the universe is constant. The change is zero. We define the universe as the sum of the system and the surroundings. So another way to put the law of conservation of energy is that the change in the energy of the system plus the change in the energy of the surrounding is also zero. The energy gained by the system is equal to the energy lost by the surrounding, or the energy lost by the system is equal to the energy gained by the surrounding. Conservation of energy. The first law of thermodynamics can also be discussed using the way energy is transferred between the system and the surrounding, specifically energy in terms of heat and work. The change in the internal energy of a system is equal to the sum of the heat Q transferred to the system and the work W done by the system. That is the thermodynamic definition of the first law. Mathematically, that can be shown in two formulas. The change in the internal energy of a system, delta E, is the energy of the final state of the system minus the energy of the initial state of the system. That is the same format we use with getting a delta H, a delta S, and a delta G. The change in the internal energy of a system can also be described using heat and work. Delta E equals heat transferred Q minus work done. This is the formula most commonly associated with the first law of thermodynamics. What tends to give students trouble with this equation, and really most thermodynamic equations, are signs. In dealing with delta G, it was the minus T delta S. For this equation, it is that minus sign connected to work. Let's take a deeper look at why it's there. It comes out of the thermodynamic definition of work. Looking at the first definition, heat, from a flow of energy perspective, heat is viewed as going into the system. Heat moving into the system is negative, and heat moving out is positive. But work is viewed as being done by the system. Work is negative when the system does work on the surroundings, and positive when the surroundings do work on the system. So for the system to gain from the surrounding, the Q has to be negative, and the work positive. Let's keep a version of that work relationship and restate how the flow of energy is related to the sign for Q and W. If the energy associated with Q has a positive sign, then heat is flowing into the system. It gains heat, and it does so at the expense of the surrounding. If the energy associated with Q has a negative sign, then heat is flowing out of the system into the surrounding. That's a loss. On the other hand, when work energy is positive, it means work is done on the system. Energy is added to the system. The change in the internal energy of the system is negative, since the formula has it as minus work. A negative times a positive is a negative. An example of this is a spring. The spring is the system. If an external energy is used to stretch the spring out, then energy is added to the spring. Energy is added to the system. That spring is now capable of doing work. When work energy is negative, it means the system is doing work on the surrounding. A negative times a negative is a positive. Energy is removed from the system. The change in the internal energy of the system is positive. An example of this is a battery. The battery is a system, and it can be used to do work. When it does work, it loses internal energy. The first law is about the flow of energy, and keeping track of that flow is not an easy job. The second law is about order. The total entropy of an isolated system always increases over time. Isolated means that there is no flow of energy or material between the system and the surrounding. The second law is consistent with our earlier discussion of entropy. The initially ordered state is always going to move to a more disordered state, and never the other way around. Using the equation for the change in entropy, entropy of the final state minus the entropy of the initial state has a second law implying that the change in entropy is always positive, which can only occur if the entropy or disorder of the final state is always greater than the entropy of the initial state. As time passes, entropy increases. Now, on a deeper reflection, that may seem to be at odds with all the order we see in the world. Our bodies are greatly ordered systems. So how is this reconciled with the second law that has everything becoming more disordered? Well, all spontaneous processes, delta G, less than 0, cause the entropy of the universe to increase. This works just fine for processes that do create disorder. But it also allows some systems to become disordered. At the same time, the surroundings become more disordered. So if we expand the system to include some of the surroundings, then the second law can be shown to be true. The example of our bodies does not violate the second law when we consider how they are formed. The order comes at the expense of the food we eat. Food starts out as highly ordered proteins and carbohydrates, but ends up as many CO2s and H2O gas molecules. Overall, body plus digestion creates more disorder. There's a statement that sums all of this up. The universe tends to disorder. Order is not an easy concept, but it is a very relevant one. For most students, the material covered so far is sufficient for their class. Some students are exposed to additional material, which is presented at this point in the lecture as advanced concepts. The first concept is Hess's law. This law, also known as the heat summation law, is limited to chemical reactions that can be written as the sum of 2 or more steps. It does not matter if the reaction of interest actually follows those individual steps. It only matters that when the chemical formulas of those steps are added together, that they generate the chemical formula of the reaction of interest. In those circumstances, the enthalpy change for the net reaction, the reaction of interest, is the sum of the enthalpy changes for the individual steps. What this rewriting of the reaction provides is a way to calculate the enthalpy change of a difficult reaction. If that difficult to measure reaction can be expressed as a series of reactions that are easier to measure, then Hess's law can be applied. But why does Hess's law work? Law of conservation of energy. The energy of the sum of the parts is equal to the energy of the whole. Another important factor is that enthalpy is a state function. It is path independent in going from initial to final state. That allows us to take any path and their enthalpies as long as they combine to give the initial to final state. That is, as long as they combine to give the reactants and products of the reaction. Let's see how that plays out with the reaction. Nitrogen gas, N2, plus oxygen gas, O2, produces nitrogen dioxide, NO2. We will call this the reaction of interest. Say we want the enthalpy change, delta H, for this reaction, but aren't able to find it or measure it. We were, however, able to find an enthalpy change for a similar reaction, in which nitrogen monoxide, NO, was produced, and an enthalpy change for a second reaction, in which nitrogen monoxide was a reactant and nitrogen dioxide was a product. In practice, the student is usually given both of these reactions and asked to find the enthalpy change of the reaction of interest. The application of Hess's law is one of addition. Add the chemical equation together in such a manner as to produce the reaction of interest, and add the enthalpy change together to get the change in enthalpy of the reaction of interest. Start with the equations. we add the reactants together, and then we add the products together. But before that, we can make the job easier by removing compounds from the two equations if a compound appears on the reactant side and on the product side. Kind of like removing spectator ions in net ionic equations. Nitrogen monoxide fits that description. It completely cancels out because there are two of them on both sides of the reaction arrows. If the coefficients are not equal, then only cancel out the appropriate number of compounds. Okay, adding reactants, 1 and 2, plus 2 O2s, forming products, 2 NO2s. This is the reaction of interest. As for adding the change in enthalpy, 180 kilojoules per mole plus negative 112 kilojoules per mole is equal to 68 kilojoules per mole. The enthalpy change of the reaction of interest is equal to the sum of the enthalpy changes of the step reactions. Again, enthalpy is a state function, and it does not matter which path or steps reactions use, as long as they sum to the reaction of interest. There are two additional points to be made with this process, and we will use the first step to demonstrate them. What would happen if this reaction were not presented to us in a way that allows us to cancel the nitrogen monoxide with the second equation? What if it was given as the reverse of the reaction, nitrogen monoxide breaking down into nitrogen and oxygen gas? The reverse reaction would have the same size enthalpy change, but with a different sign. One way the reaction consumes energy, the other way it releases it. As written, this equation will not directly add with the second equation to sum to the reaction of interest. Reactions and products are on the wrong side. No problem. Simply flip the reaction and change the sign on the enthalpy. The enthalpy is now a positive value. It is ready to go back into the summation of reactions. A second issue comes up if the summation of the reactants and products of the step reactions do not produce the reaction of interest or do not get the coefficients correct. Often this is because there are not enough of or too much of some compound. This is handled by multiplying or dividing a step reaction by some whole number. For example, say in the first step reaction, the amount of nitrogen gas needed to be doubled. This can be accomplished by multiplying the entire reaction by 2. Note the parentheses are also around the change in enthalpy value. Multiplying everything gives a modified set of coefficients and a modified energy term. Using Hess's law is somewhat like doing a puzzle. The pieces are moved around, maybe flipped, but in the end, the puzzle only goes together in one way. A final note. The process described here works with state functions, delta G and delta S. Same exact logic. Get the reactions to sum to the equation of interest and add the state function values. The other advanced concept topic is enthalpy of formation. That is given the designation delta H sub F or delta HF. It is the enthalpy change, and that can be heat released or absorbed when 1 mole of a compound is formed from the combination of its elements. In other words, the enthalpy of building the molecule from atoms. We will limit the discussion to the standard enthalpy of formation, delta HOF. It is the delta HF at standard conditions, 25 degrees Celsius and 1 atmosphere pressure. The subscript O or 0 refers to standard state conditions. Important to note, elements themselves have a delta HOF of 0. That is, it takes no heat transfer to make an element. And that goes for the elemental form of that element at standard conditions. Oxygen is found as O2 under standard conditions. O2 has a delta HOF of 0. Conveniently, the standard enthalpy of formation of a compound is found in a lookup table. These are not things derived from mathematical formulas. They have been measured in a lab. Most textbooks have tables in the appendix section of the book. Just so that we know, the more negative the standard enthalpy of formation, the more stable the compound is. The standard enthalpy of formation can be taken one step further. The heat of reaction under standard conditions, denoted by delta H O reaction, Rxn. It is calculated from the sum of the delta HOF of the products minus the sum of the delta HOF of the reactants. In a format similar to that seen with other state functions, heat of reaction under standard conditions is a sum of the standard enthalpy of formation for each of the products minus the sum of the standard enthalpy of formation for each of the reactants. Fortunately, those are gotten from the lookup table. So this calculation is really just finding the compounds in the reaction in the table and summing those energies. Well, almost. A couple of examples will give us a clearer picture. What is the standard heat of reaction that has sulfur dioxide plus molecular oxygen forming sulfur trioxide? This is a pretty stinky reaction. It is not necessary, but to make a point, we will rewrite this reaction so that all the compounds have a coefficient of 1. That means sulfur dioxide is written twice, as is sulfur trioxide. We will use this second version of the reaction to find the standard heat of reaction, and then show how it's easier to calculate using the first reaction. To get the standard heat of reaction, find the delta HOF for each compound in the reaction. Use the lookup table, starting with sulfur dioxide. If we went to the table, we would find a standard heat of formation of minus 296.8 kilojoules per mole. This value holds for both sulfur dioxides. The next compound is oxygen. It is in its elemental state, so it has no standard heat of formation, 0 delta HOF. The last compound to find a value for is the sulfur trioxide. According to the table, its standard heat of formation is minus 395.7 kilojoules per mole. That holds for both sulfur trioxides. Notice that the sulfur dioxide and the sulfur trioxide have negative standard heats of formation. They are both stable compounds, with sulfur trioxide being more stable. With our heats of formation in hand, we are ready to calculate the standard heat of reaction. Start by getting the summation of the standard heats of formation for the products. That's these guys. Add all values together. Add negative 395.7 kilojoules per mole twice. One for each sulfur trioxide. So this part of the calculation is in order, but it can be cleaned up some if we look at the original equation and see that it has a coefficient of 2 for the sulfur trioxide. Instead of adding 2 standard enthalpies of formation in the summation, we can also use the coefficient as a multiplier. It is the same thing, only easier to follow. Now to subtracting the standard heats of formation for reactants. And this summation begins with the sulfur dioxides. We need 2 of this delta HOF. These can be added individually, like this, or returning to the original equation, use the coefficient as a multiplier. Same thing, simpler equation. There's one more reactant to deal with, oxygen. The nice thing about this compound is that it has a standard enthalpy of formation of 0. That can be included in the summation, but since it's 0, it can be ignored. The equation is complete, and the last step is to do the math. There are many places to get in trouble with sign errors. Doing the equation in parts is a good idea. If the math is done correctly, a standard heat of reaction is gotten as negative 197.8 kilojoules per mole. Is this reaction exo or endothermic? The change in enthalpy is negative, and that means exothermic. One more, and it's a combustion reaction. It solves the same way. Get a standard enthalpy of formation for each compound. In this step, we will ignore the coefficient, but it will be used in the summation step. The first reactant compound is methane, and from the lookup table, the delta HOF is found to be minus 74.81 kilojoules per mole. The other reactant is oxygen, and it is in its elemental form at standard state conditions. It has no enthalpy change. The first product compound is carbon dioxide. It is a stable compound with a large delta HOF. Finally, there's the product water. It too is a stable compound with a standard enthalpy of formation of minus 285 kilojoules per mole. With that done, it is time to set up the standard heat of reaction equation. It starts with the summation of standard heats of formation for the products. Now the coefficients come into play. First, the carbon dioxide. It has a coefficient of 1. Take a single value of its delta HOF and add it to the summation of products. Square brackets are used to combat sign errors. The other product is water. It has a coefficient. Take that 2 along with the minus 285.8 kilojoules per mole to the summation. That completes the summation of enthalpies of formation for products. Now, to reactant. Methane is up, and it has a coefficient of 1. So just 1 of the minus 74.81 kilojoules per mole is added to the summation. The last compound is oxygen. It has a coefficient of 2, but that doesn't really matter because it has no standard enthalpy of formation and brings no value to the summation. All values have been included, and what's left is the math. This time, we will do it in parts. The summation of standard enthalpies of formation for products comes to minus 964.5 kilojoules per mole. For reactants, it is minus 74.81 kilojoules per mole. Negative 964.5 minus negative 74.81 is minus 889.7. It should not be surprising that a combustion reaction releases so much heat. And that concludes the material of the lecture. To the recap. A review of thermodynamic material opened the lecture along with an introduction to the state function. It relates the properties of a system that only depends on the initial and final state. That transition is path independent. 3 state functions were covered in this lecture: delta G, delta H, and delta S. The first of those state functions is enthalpy. It is defined as the internal energy of a system plus pressure times volume. A more useful definition is the heat content or total heat. It is also used to characterize whether a reaction is exo or endothermic. The change in a state function, as related to a chemical reaction, is often shown as the difference in the energy of the products minus the energy of the reactants. Final state minus initial state also works. The next state function was entropy, capital S. Its definition is the thermal energy that is unavailable for doing useful work. The more useful definition is that it is the measure of the disorder of a system. Disorder releases energy. Order takes energy. 2 formulas were given for entropy: S equals Q over T, and the state function definition. The change in entropy is equal to the entropy of the final state minus the entropy of the initial state. The last of the state functions is Gibbs free energy, capital G. It is the energy associated with a chemical reaction that can be used to do work. It also has a state function formula, but its real power lies with how it relates the enthalpy and entropy. G equals H minus T times entropy. Expressed as the change of energy in a reaction or a process, it indicates the favorability of a reaction. We also covered two laws of thermodynamics. The first law says that the change in the internal energy of a system is equal to the sum of the heat transferred to the system and the work done by the system. The equation is delta E equals heat minus work. The second law deals with entropy. The total entropy, delta S, of an isolated system always increases over time. In other words, the universe tends to disorder. There was also a couple advanced concepts in this lecture. Hess's law, or the heat of summation law, is limited to chemical reactions that can be written as the sum of two or more steps. In those circumstances, the enthalpy change for the net, or whole reaction, is the sum of the enthalpy changes for the individual steps. The other topic was the standard enthalpy of formation, delta HOF. The standard heat of a reaction, delta HO reaction, is calculated by summing the standard enthalpies of formation for all products and subtracting the sum of the standard enthalpies of formation for all the reactants. And that concludes the lecture. Thermodynamics follows the flow of heat and work in a reaction.